right. So let's get started here. Hi, everyone. This is the using motors and gearboxes presentation. Thank you for joining the summer series here. And I guess we'll get started right now. All right. So a little bit of background on me. I've been doing FRC since 2014. I was design and engineering lead for Team 5199 from 2016 to 2018. And ever since I graduated in 2018, I've been a design mentor, helping out the team and doing stuff like gearboxes. So basically, this presentation is mostly just going to be kind of me sharing my kind of personal, not necessarily opinions, but experiences with designing gearboxes. I tend to do kind of a seat of the pants kind of design philosophy in a lot of ways, just because we have such a crunch design season. But this is kind of just my perspective on the ways to design and spec your gear ratios and motors. So I guess we'll get started with the basics, just to quickly make sure everyone's up to speed. This is kind of your, also at the very end, I'll have questions at the end. I tend to move kind of fast, as you can already tell. But if you have any questions, please, put them in chat, and I will try to address them as they come up or at the end as well. So this is your basic motor. Input. You usually have about 2 input wires, your output shaft, and your mounting holes. Some new developments have been, brushed versus brushless motors. For a long time, brushed were, the most common in FRC, but now brushless motors are coming up. They offer, a little bit more efficiency and power, but they have a special controller. And we can go into this a little bit later if you have some questions on that, but I'll just kind of leave it at that for now. In your gearbox, it's composed of, 2 main parts. You have your motors and your gear ratios themselves. This is a 2-stage gearbox because you have your input stage and your output stage. Sorry, you have your first stage and your second stage. Your input gear is usually called your pinion. So if you see that in documentation, that's your small gear. Your big gear, sometimes called the bull gear, is usually the output. If you're gearing down, if you're gearing up, you'll be going the other way. So a common question I get from people is, why gearboxes, right? We have these electric motors. They're relatively powerful. So why do we need a gearbox? Well, electric motors in and of themselves usually have very high RPMs and pretty low torque at the actual output shaft. Like, I don't know if anyone's ever taken a raw electric motor, but I wouldn't recommend doing this, but you can actually stop it with your hand in most cases fairly easily with a small handheld motor. But you can put it in a gearbox and obviously it becomes much more powerful, much more usable. And additionally, the output shaft is usually relatively small, because the motor itself is fairly small. So it's kind of hard to mount to that. So in actually doing your gearbox, gearing is actually relatively simple. It's just based on the ratio of your small gear to your big gear, or, of the gears to themselves. They can be thought of essentially as circles of 2 different diameters. So when you put them together, you get kind of this ratio effect of the small and the big. And actually, very old reduction systems involved, just simply 2 friction surfaces that were just circles rolling together. Teeth were added, to prevent slippage, and allows you to transmit significantly more torque. So moving on from there, you can see that the gears themselves have different circumferences. This is what we're going to learn is called a pitch circle. And this is actually, kind of like the midpoint, the point where the 2 gears are tangent to each other. And this is equal to your gear ratio, right? So your radius is related to your circumference. So your circumference and radius are kind of combined and they equal your gear ratio. And you can see This small gear would have to move 2.375 times to match the distance of the green gear, right? The big gear, which means that this green gear will move 2.375 times slower than whatever your input is, right? So your output shaft moves slower than your input shaft because this needs to spin more, go farther than the big one, right? And so this is what gets you your speed reduction. Now, most of the time, speed reduction is kind of a byproduct to what I see as the ultimately more important part of a gear system, which is your torque change, right? So a gear, you can kind of think of it as two different levers, right? Because, torque is just a force at a distance from your rotation center. So if you have a small lever pushing on a bigger lever, you get more mechanical advantage from the input shaft on the smaller gear to the output shaft on the bigger gear. And of course, this works in the other way as well. If you end up, gearing to increase speed, you lose torque because now you have a longer lever pushing on a shorter lever, right? So you lose that mechanical advantage here. And so this is one of the major advantages to having a gear ratio at all, is that you can actually take these high RPM but very low torque motors and change them into a slower RPM but significantly higher torque output. And that's kind of the whole idea. So the key ideas when kind of thinking about gearboxes is power in and power out. This is what I found was the most important thing when I was learning. I was thinking, how do these small motors, right? Why can't I just use a tiny motor instead of, a big motor, right? If anything can be geared to any torque, right? Because theoretically, any motor can produce any torque as long as you gear it enough. Well, no matter what, the smaller motor will always have less power, right? So power in equals power out is one of the most important things, because you will never get a small motor that is extremely fast and has high torque at the output of your gearbox. You have to sacrifice something, right? There's no free energy in this equation here. So if you have a bigger motor, you can gear it down less, you maintain a higher speed while also outputting a similar torque. And we'll go into this a little bit later in the presentation when we go over actually kind of looking at calculations of the gear ratios. But yeah, the main thing is, there's no free energy in this equation. A bigger motor will always have a faster and higher torque output. Ratios are easy to calculate. Like I showed before, it's just a ratio between the input gear and output gears. So if you have a 20-tooth input gear and a 40-tooth output gear, 40 over 20, that's 2-to-1. Your speed will be halved because you divide it, and your torque will be doubled because you multiply it. These concepts also apply to belts and chain. So if you have, say, a 20-tooth pulley and a 40-tooth pulley, it's the same. It's a 2-to-1 ratio, and the same concepts apply here. So what are your options when you're kind of designing a motor for FRC, right? Well, there's only a select number of FRC legal motors. These motors are defined in the rules. It makes your life both easier and harder, I would say, because you have less of a selection, which puts you in kind of a difficult position because some of the motors, you just space gaps in between power levels and sizes and things. But it's also easier because you don't have to wade through a million different motors to find the one that you want. VexPro has a really nice list with really helpful data. You can find that at motors.vex.com. I would say that's, when you're designing a motor, that's a, one-stop shop, very easy, especially if you're buying your motors from Vex. They give this very helpful list. You can dive into each of these motors. They have really helpful graphs that we'll go over later. But yeah, we'll come back to that later in the presentation. Okay, so types of gears. There are what are called spur gears, right? That's your classic, if you look at a picture of gear online, you'll find, toothed, single plane, one gear touching another gear, that's your simple spur gear right here. It's easy to make custom reductions. Like I said before, the ratios are just equal to each other. Many COTS gearboxes come with this. These gears are usually fairly large, but you make up for that with their high strength. They're relatively easy to package. I mean, this gearbox here, you can see it's just, 2 shafts on a plate. And they're often pretty cheap because they are such simple two-dimensional shapes. You can buy a lot of pre-made gearboxes with this configuration. Where you have your pinion gears as the one I showed before. And yeah, these are usually, kind of the more common option when you see teams make their own custom gearboxes. But if space is at a major premium, planetary gearboxes offer a couple distinct advantages, but also a couple drawbacks. The main advantages are they are extremely small and extremely low weight while they are dense, because you have a reduction that happens using this planet and sun system. I'm not going to go into that a lot right here, although I would encourage, looking a little more into the theory and calculations behind that if you want to later. But it's a very neat system that gets you massive reductions in a small space. In the same space, you can get a 3-to-1 reduction. You can also get a 10-to-1 reduction. But because of this, they are lighter duty, while you do make up for that with their space efficiency. But I wouldn't recommend using these for anything that has a high kind of impact output. And because you can see, they have a lot more moving parts and a lot of, small shafts in here that couple things. And just the movement is a lot more complex, so they can be significantly harder to repair if they're repairable at all. Oh, another interesting option you can think of are shifters. I'm not going to go into shifters and the selection of them right now, but it's basically just 2 different selectable ratios. You can see this is what's known as a dog shifter. It's a little bit simpler of the 2 options. You can probably make this with just a drill press and a simple mill, but you can easily see how it's just 2 different ratios that connect to each other. So you can use the same calculations that we showed before. And then another thing is a ball shifter. There's really one main COTS option, which is from Vex. These work in a different way. I would recommend looking into the Vex website if you want to see how these actually work. Once again, you're just selecting 2 different gear ratios, and so all the calculations that we show later in this presentation will also apply to the 2 different ratios in here. Okay, so the kind of meat of the presentation here are the design considerations. So once again, if you have any questions, make sure to leave them in the chat, and I can come back or I can slow down. But yeah, this is the most important part for sure. So the first thing to do at any state of the design process, and especially for gear ratios, is to define your loads on your mechanism, right? So in this case, what's helpful to have are, say, the length of the arm that you want to drive, or your drive wheel diameter and the weight of your robot if you're doing a drivetrain, or the pulley diameter if you're doing a elevator or climber if you're using like a rope system. These are all needed to calculate the gear ratio to find the force needed or the torque needed to properly move your mechanism, right? So torque is very important. Without torque, the robot will not move, and I'll go into that a little more in a second. So speed is the other option, right? So when you pick your gear ratio, you're balancing your desired speed and your needed torque, right? So what's interesting about this is speed, while it is really important to have, a high-speed mechanism, we're in a competition scenario. If a mechanism is geared for too high of speed and doesn't have enough torque, that mechanism will never move at all because the motor will not be able to move your load. So if it's the choice between having the speed you want and the torque you need, you always have to pick the torque you need because if there's not enough torque, the mechanism simply won't move at all, and that speed will essentially be unusable, right? So, in this case, oftentimes, the team will decide, a target drive base speed or a target elevator speed or an arm speed, and you will base your calculations off of all these in the future. So it's good to know what kind of your goals are so you have something to shoot for when you're designing. In terms of weights, you want to take into account everything that you can foresee, not only, the game piece, but also the mechanism, how much safety you want to give it, in case you might accidentally have a second game piece that you need to move out of the way, your robot weight, robot weight with pushing another robot, all kinds of things like that you want to make sure you consider. Something else that's important is kind of just general stuff, wear and impact. These can really determine which types of gears and gearbox you want to use. Like I said before, the planetary gearboxes, small and light, but also easily breakable and almost impossible to service on the field. So, you want to take that into account when you're designing your gearboxes. Additionally, same thing, you balance between your space you have versus, what you need. And sometimes, you have to go back and make sure that, your thing not only fits, but also won't break on the field. Something that's nice is almost all motors and off-the-shelf gearboxes have CAD supplied. So, make sure to use those when you're actually designing. A lot of times, you design your mechanism and you'd be like, okay, I'll just put the motor here. But, you want to make sure you actually put that motor in CAD in your design, draw it out at least in 2D, and make sure you can get enough space, especially if your motor is moving on, say, an arm. Another thing, there's many different motor sizes, and as I'll show in a minute, a lot of motors are, radically different sizes, but have the exact same power, right? So power in, power out, they have the same power, but you have to figure out, okay, would I rather use the larger motor and have a little bit easier gearing, or would I rather use the smaller motor? It really depends, if it's in a weight critical place. And this is really kind of where your job as a designer comes in to figure out what is ideal for your situation. So this is on, a case-by-case basis. And I'll show a calculation later using a calculator where you can really see the difference between a small high-speed motor and a large low-speed motor that have the same power, and what kind of difference that makes for your gearbox. Okay, so most important part, I think I said that before, but this is definitely the most important part of the presentation. If you take nothing else away from this meeting, you definitely need to check out the JVN design calculator. This is something made by, I believe his name is John V. Noon. He's from the Robo Wranglers. He has a great calculator. It's completely invaluable. It is the most important thing you could ever use when you're doing these quick iterations and calculations. It has lots of tables in there for all kinds of different stuff. You really don't have to, dive into the theory right away if you don't want to. You can just get an answer if you need one quickly. But once again, if I would encourage looking into the theory because it helps understand these calculations a bit more. It's to find this calculator, it's usually best just to Google, JVN gear ratio design calculator, because he does tend to update it as new motors come out, and especially recently as we've been having, kind of an influx of new brushless motors. He can, usually add those or update them. So I'll kind of go into how to use this calculator right now. It's very simple, but I'm just going to kind of provide an overview and then my process that I use when using the calculator. So the first part is to, you can kind of look at these different pages that they have in here for the different mechanisms. There are tabs for, linear mechanisms, rotary mechanisms, drive bases, all kinds of stuff. And you can see, just the amount of information that it gives. You can input your motor type up here. It'll automatically populate all these boxes. And then any of the boxes with the kind of red, orange looking color, those are actually inputs that you put in, your parameters in here. So you can see, this is why it's so important to know your loads before going in, because see, this requires, how heavy of a linear mechanism or how heavy of a robot do you expect to pull, or how long is your arm, what's the weight. And then additionally, this is where you actually play around with gear ratios down here. It also offers some easy configurations for commercial off-the-shelf gearboxes, mostly for just VEX products because they're kind of more related to that. But yeah, you can see, once again, you got to know your wheel diameters before going in, your friction, all kinds of different stuff in here. And then you just kind of iterate through and get your outputs. And we'll go over how to read these outputs in a second. Another thing that's nice is, you just look up, motors once, if you need to add a new motor, you can put them in here and you can see all of these. You don't have to go to the website every time you want to see the motor specs themselves. They're all contained in the calculator. So as new motors are added throughout the season or between seasons, you can easily put them in here and they'll pop right in and all the calculations will be done for you. So now we get to the part where, you decide, which motor is actually good for your particular application. And this comes from, the outputs that it gives you. You have to verify the outputs and make sure it has your desired result. So you can see here, the outputs look, they look the same for most of them. They have a drivetrain output one, which will show your drivetrain's free speed. This is showing for a 2-speed gearbox with your different ratios here, and shows your expected robot speed. And then also for something like an arm or a linear mechanism, you can see what your max load will be and what your current draw will be. So something to keep in mind when you're reading, especially something like current draw or stall load, is that there are breakers on the robot. And so if you see this number, is over, say, 40 amps for the large breaker, you will end up blowing your breaker if you're constantly loading at 40 amps. So you have to keep that in mind when designing your gear ratios, is that while the motor will technically work at those, it may end up being detrimental to robot performance. Additionally, the stall load, that's where your mechanism stops moving at all. So if you see the stall load, it's not 28 amps at 754 pounds. It's 28 amps at the load you put in, and 754 pounds is where your motor will simply stop moving and the whole mechanism will stop. So your actual load should be much less than the stall load you see here. If it's too close, you run the risk of any kind of extra loading causing your mechanism to stop and or even burn out motors in some cases. So how do we actually determine what this current draw means for each motor? That is done through something called motor graphs. So motor graphs are something that are relatively important to read, that often aren't brought up when first designing motors. They really give big insights into motor performance and can help you determine where you want to gear your motor, because all motors like being in a certain area and don't like being in another area, as I'll go over in a second. And this can literally make or break your design, right? So motors, we all know they burn out. And sometimes it feels, kind of like a mystery as, why is my motor burning out here? It moves the mechanism okay, but it's getting really hot. And this motor graphs are a way to show you, a relatively accurate representation of what your motor will be doing at any given load. So to find these motor graphs, I'm going to be showing you how to do it through the VEX website from motors.vex.com. Often, if you're using a non-VEX motor, the graph will be given on the motor's data sheet, or they will just simply give you max power. And I'll show you in a second how you can estimate these graphs based on max power itself. So something to keep in mind here is that these are done by VEX. So, there are some non-VEX motors on here, like the Neo motor. And so you'll see slightly different numbers based on where you get your sources from. Just keep that in mind. It may be a good idea to take an average of those. But for right now, we're going to go over the 775 Pro motor, just because that, it's an interesting motor to look at, and they have a lot of good data on that motor. So when you're on motors.vex.com, you will see 775 Pro, and then if you click on that, it'll open up a page with all sorts of information, right? It'll show you the information that they found from their testing up here, the very basic information showing, their max power, current and stall current and torque, and then the actual motor graph itself, as well as some other really helpful information over here. This is kind of outside what we're going to be talking about here, but if you're wondering why the 775 Pro tends to burn out easily, these graphs are helpful to find out that information. But the motor graph is really what we're going to be concentrating on here. So if we zoom into that, you can see that it consists of lots of different kind of lines themselves. And so you essentially have 4 different graphs on this one graph. Efficiency is the red dotted one. I usually don't worry too much about that, just because we'll usually be operating in this region anyways, as I'll explain in a second. You can see that current is highest when your motor is locked, and your stall torque is also the highest when your motor is locked. But your power, and this is output power here, your power increases until about the midway point and then decreases as you get up to the highest RPM zone. So what's interesting about this is, okay, if I run my motor in this region, or if I run my motor in this region, it'll have the same power at any given point, right? Because it's a parabola. So which region do I want to be in? Well, if you take into account current, you can see that this zone is a lot safer for the motor than this zone over here. All right. So if I am running the motor at, say, right here, this looks like about 300 watts of output power at about 13,000 RPM, it's only going to draw about 40 amps. Whereas if I try to get 300 watts of output power at 6,000 RPM, that's going to be drawing almost 100 amps, which will almost certainly burn out your motor and will trip your breaker very quickly. So when you're designing a motor, you want to be operating it in this safe zone over here. And so what's interesting about all electric motors is they all DC motors pretty much have this same graph here, where there's a high power zone past and before will be at the same point. So you always want to kind of design for this part here. Okay, so let's say you want to verify your output using this motor graph, right? So we'll move into the calculator again. So you put in your physical constraints, make sure you're working on the right calculator, put in your motor, put in your gearing, and then you'll see your output right here. And so these are your most important parts. So if we zoom into those, you can see here, okay, here's your current and here are your speeds, right? These are usually the two, and your load. These are usually the things you're looking at when you're actually designing your motor, your gearbox. So once again, the speeds are important, but they're usually a byproduct of your kind of maximum load case here, right? So let's say we have this motor at 42 amps, and it's a mini sim motor. We want to see if this is in the safe zone of the actual motor itself, or if this is something that's going to burn out the motor, right? So we move to the motor graph, and we cross-reference our amperage and our motor graph. So if we come over here, we can see this is the current axis as well as the power axis. And so we'll find 40 amps, and we'll move over to where the 40 amps are on this line, right? Because this is our current line, right? So we know that at 40 amps, it'll probably be running around like 3,200 RPM. And then we move up and we find that, okay, It is in the second half of the curve, but it is quite near the top, right? So you can imagine if a load over the one that we put in before, it'll increase our current, and we'll start moving into the kind of more dangerous zone. We'll actually start losing power for our motor. So it might be better to actually gear our motor farther down on this curve. So that way we have, if a higher load comes in, we actually gain power to compensate for that load, as well as not risk burning out the motor itself. So these graphs are very important to read and are really helpful in designing a successful and also safe mechanism. This basically just kind of reiterates what I said before, but also, takes into account, if your motor's too small, you may never actually get the performance you want out of it, right? So any motor can operate with enough torque in its safe zone. However, its speed will suffer if its power is too low. So that's, when you're sizing your motor, you really want to figure out what your lowest acceptable speed is. And that way, if weight is important, you can pick a smaller motor and use its power to the fullest. Whereas if you oversize your motor, you might be having something that's too unusably fast anyways, and is just increasing weight. So that's something to keep in mind when you're designing that. Same thing with efficiency. I'll show this in a second too with my example, but your input and output RPM, right, as I mentioned at the beginning of the presentation, they're based on your gear ratio, but they're also based on your motor. So if you have a very high RPM motor and a low RPM motor, then what's going to happen is you're going to have to gear down the high RPM motor more to get the same output speed as the low RPM motor. And that can lead to kind of some interesting problems, because some motors have the exact same power but higher RPM, and I'll show that in a second. Same thing with efficiency. So, you want to make sure that, you pick gears based on, what you're kind of working on. I mentioned planetary versus spur before, custom versus buyout. This is a big one. If you don't have the time to, design or the resources to design an actual, custom gearbox, it can be useful to, just buy one out, but you still want to know, do I want a planetary or do I want a spur gear? And then additionally, kind of weight considerations and strength that go along with those themselves. Let's see here. Oh yeah, once again, make sure to check in CAD. This is an issue that we've run into before on Robot Dolphins is, it looks like it's going to work, and, everything seems like it's going to work, and you put it in CAD, it doesn't quite work. And, that's why it's really important to make sure your space constraints are met when you're designing that. And then another thing is iterating. So usually you'll never get the gearbox perfectly right on the first try, or your gear ratios right on the first try. That's the beauty of using the calculator that I was showing before, is you can easily go back and, keep changing your gear ratios with, a couple keystrokes, and you can really, tune in your gear ratio along that motor curve. So you can see, if we are designing something that we know will have a constant load, it might not be good to be this far down on the curve because you're not getting maximum power. Whereas if there's something where you don't expect getting, a higher load and getting pushed back in the curve, then you can easily design for up here and extract more power, more speed out of your motor while still maintaining enough torque for to actually move your mechanism. Okay, so I'm going to give a quick example, and then we'll move into some questions after this. So in this example, we're going to be doing a really simple robot arm. I'm going to kind of simplify things here and say, only brushed motors. We're going to use a 775 Pro and a Sim. We're going to compare those two for this example. We're lifting a 5-pound game piece with a 20-inch long arm that weighs 15 pounds, right? And we want to say, okay, speed is important as always, so we'll try to maximize that. So looking at the 775 Pro and the Sim, the sizes are kind of deceiving here just because of the picture, but the 775 Pro itself is a significantly smaller and lighter motor than the sim. And you can see this reflected in the free speed. This is a significantly higher speed motor. It has a lot less inertia on its rotor inside, and so it spins up a lot faster. Whereas the sim motor is a lot slower, but it has a higher initial torque. But what's interesting to note is while these motors are, massively different looking, their power is almost exactly the same. They're within, a couple percent of each other. This is only 10 watts more than this. And so it's interesting to note, looking at maximum power, what is going to be the difference in these motors when you're actually designing your gearbox? So we'll plug it into the calculator. And you see when you plug it in first, you just select from the drop-down menu, puts in all the information here, and you can see right away why we need a gearbox, right? The stall load for this thing with our arm length and our arm load will only be, a fraction of a pound, right? Because of the torque disadvantage that we have because of the arm length. So we need to start playing around with gearing and see what we can have happen. Something interesting that you'll note is that I actually didn't put, 15 plus 5 here. I actually doubled that. And that's because I'm adding a 2x factor of safety. Another thing to note is technically because of the way that the weight is distributed along the arm length wouldn't actually be 20 inches. But once again, for safety, I'm leaving that higher because that'll increase the load that's seen in the calculator, and we'll just kind of add a safety factor to your mechanism. That's something that you can change if you need a little bit more accurate performance, but I like to do this just to be safe. So you can see I've now geared these to have basically the same current draw per motor. But what's interesting to note is that look how much higher the gear ratio has to be for the 775. It has to be 440 versus 135 for the sim motor. And this can be interesting when you're trying to design a spirit gearbox because you'll probably have to add a lot of extra ratios in here. Now you can see here I've just simplified it and just used planetary gearboxes, but planetary gears often aren't the strongest for something like an arm. And if you're seeing that you might take impact, it might not be a good idea, especially to use a high gear ratio on the output. So in this case, if you had to use a planetary gearbox, might be a better idea to go with the sim because you can get that lower output ratio here. However, in most cases, you'd probably want to use the 775 because of its lower weight, even though you probably have to gear up more. And that's really something that is dependent on kind of your robot goals and your packaging requirements. But it's just interesting to note that they have the exact same speed, exact same current draw, almost exact same stall load, but it's the gear ratio that really drives the difference here. Whereas, power is the same. And so kind of last thing I'm going to go into here, I'll go through this quickly just so I have enough time to answer a question or two. Basically, when you're designing a gearbox, it's relatively easy to actually prototype your gear spacing, right? Because gear spacing is extremely important. So gears, once again, are just basically circles. And there's a specific name for this, quote unquote circle, and that is what's called the pitch diameter. You can find these, on your manufacturer's website. And so you want to make two circles that are equal to the pitch diameter of the gears and make those circles tangent to each other. And so I'll show you how to do that really quickly. So this is the Vex Pro datasheet. You can see here the pitch diameters are all given, and they're just, it's a diameter of the circle. You can see the pitch diameter is represented as this inner circle here. And so if I wanted to say put a 20-tooth gear with like an 80-tooth gear, or 24-tooth gear with an 80-tooth gear, I just take those pitch diameters and make two tangent circles, and that gives me my center-to-center distance between those two shafts. And so this is, you just got to keep this distance rigid to each other, and that's basically how you design, how you properly mesh these two gears together. Now, you can play around with different meshes to get, different kinds of things like backlash or wear considerations. But once again, for just an intro thing, I think this is the key to, simply putting two gears together. All right, so I'll answer some questions quickly so we don't run too far over time. Okay, so when would you use 32 DP gears versus 20 DP gears? Okay, so DP is your diametrical pitch. That's basically saying, we have, these two circles, but how many, if you can put a lot of teeth on here or fewer teeth on here, right? And so you can imagine with a 32 DP, you're putting more teeth per diameter increase, right? So your teeth are smaller. So you can get a lot of teeth on a really small gear. Let's say you want to put it on a 775 shaft, right? You can get, say, more teeth than you'd be able to with a bigger gear or with a bigger DP, with like a 20 DP. But you sacrifice strength because each individual tooth is smaller. So usually you'd use a 32 DP gear when you want to have a gear that's physically smaller with a smaller shaft size, but strength isn't as important. Okay, so another question, is there a good way to remember which motors go with different mechanisms? So that's kind of a hard question to answer because, motors are so dependent on the actual mechanism. But a good rule of thumb is if you want to avoid gearing down, go with a larger motor like a sim or a sim equivalent. But if you have, something where your motors might be stalling out a lot, that's good to have. But if you want something to run high speed, say a shooter motor, you want to pick a higher speed motor for that, such as a 775 or like that new 550 motor that just came out. All right. There's no other questions. I believe that's it for time. We will be back in a minute with the mentoring to make a competitive team panel. And I'd just like to thank you all for coming to the summer series today.
Welcome to the 2020 Summer Series. I'm Jack Fallon from Team 5199, the Robot Dolphins from Outer Space, and I'm going to be your moderator for today. Today, on day 3 of the summer series, we will be discussing mentoring and the different strategies mentors can use to make a competitive team. Also note, you do not have to be mentored to learn from today's workshop. There will be tons of strategies that a team as a whole can use to improve. We are welcomed by panelists from Team 3309, the Firebots, Team 3476, Code Orange, and Team 5199, the Robot Dolphins from Outer Space. All panelists today were selected as top mentors as Woodie Flowers finalists, so we should be in good company today. Panelists, would you care to introduce yourselves?
Go ahead, guys.
Sure. I'm Evan Smith from Team 3309 Firebots. I'm an engineer at Boeing for 32 years. I do airplane modifications there. I was introduced to the team in 2012 by our founding father, Dr. Carr. And at that time, both my sons were going to the school, so I thought it was a good idea to spend more time with them. So that's kind of how I got started. Won the Woodie Flowers Award in 2015 at the Los Angeles Regional, and that's about it for an intro.
I guess I can go. My name is Rick Jung. I'm on 5199. I have a degree in industrial design. I'm not an engineer. It's a related field. I'm also owner of a product design office consultancy. I've been on the team since 2016 and became lead mentor, I guess, in 2018 until present. I also have been racing cars for a long time. That helps bring some of that experience to the table too. Let Saikiran go.
My name is Saikiran Ramanan, and I'm a mentor on 3476 Code Orange. I started off as a student on Team 696, the Circuit Breakers, from 2011 to 2014. And when I went to UCI, I started mentoring Code Orange from the 2015 season to present. I mentor in a wide variety of spaces, but I'm currently an engineer at Northrop Grumman, and I do electrical engineering there.
Thank you. Also note, please drop questions in the chat. We will be addressing all of them. So if you have any questions for the mentors, please feel free to drop them in the chat. Right now, we're going to go with some prepared questions. So the first question for today is, what is the biggest thing rookie teams can do to become more competitive?
Well, I can speak about not necessarily rookie teams, but kind of the two major things we look at in the beginning or before even the season, just from a philosophy point of view. So we look at FRC, we look at the C in FRC, which is competition. So we try not to get trapped into thinking this is a science project or an engineering competition. It's really the sporting activity. So we try to focus on the ranking points. The second thing we do, which has to do with, it takes a lot of commitment to be on a team. We ask the team in the very beginning of the season, do we want to be competitive? And usually the answer is yes. And then that goes along with knowing it's going to take a lot more work. If you want to try to play at the top, it means you got to put as much work in as the top teams. So it usually comes through during the season when we start getting bogged down to remember that. But go ahead, guys.
Okay, I'll go next. Well, I would say that engaging a team that's in your community that can mentor you, and you can learn a ton of stuff and skip through a lot of the pitfalls by connecting with a team in your area, maybe 2 or 3 teams even, so you get a different idea of how teams are run and what they focus on.
Actually, to piggyback off of what Evan said, I think that's the most important part, right? Not being too involved in your ideas, kind of, but try to look at what's in the community, especially as a rookie team or as a newer team. You don't have to reinvent the wheel, right? You don't have to do everything yourself. You should, reach out to other teams in your area that might be able to help you. Look at Chief Delphi. Look at the very basic designs, like every bot out there, or the minimum competitive concepts put up by different organizations, and like take inspiration if you're a rookie, right? This is the year for you to learn and to try to figure out what's going on before, you can make like a amazing ultra competitive robot. And doing that kind of stuff doesn't preclude being really competitive either, right? I think in North Carolina, like the one regional that went, the first seeded robot was an every bot, and they won the event with an every bot. So it's a very legitimate and valid strategy as well. So that's what I'd recommend, kind of approaching it with an open mind.
Thank you. We already have some questions popping up in the chat. Rick, we'll get to you after Ali, but we have a question from Ali. I mentor, get my freshmen and new members excited about the program.
Guys.
So I can take that as well, going back to back. I think that we all know that robotics meetings are fun, but where we all get really into it is the competition. That's what really gets us all excited. And I remember as a freshman, right, going to meetings was fun, but I think it was either a regional or fall classic back in 2011. That's when everything kind of like clicked for me, right? That's when you saw like, oh, it was just more about our robot. It's about the entire community. So I would recommend, I mean, it's hard to do competitions right now, but when hopefully things open up again, that's what we find works, getting people excited for competitions.
Yeah, when we start at this time of year, we really start pushing our new members and especially the families to get ready to go to off-season competitions, because typically what happens is you build season, and the first time the families go to see what's actually happening is after the build season, and then it goes, oh, no wonder you guys are working so hard. So it helps get everyone to buy in and get to a off-season competition early.
Yeah, I think it's the same thing. The off seasons are key to building that excitement and seeing the grandness of the event, and the students get real excited about that. So they get enthusiastic about continuing on, and that's it.
I'd like to hear more about your guys' team, the background before we get too far into it, so people know. We've been playing you guys for a long time. So Code Orange helped us out when we first started too. But I'd like to hear a little bit more about your competition record and how far have you gone?
3309, you're the oldest one here. Do you want to start off with it?
Sure. This is our 11th year, and we have about 9 blue banners now. We won 4 regionals, and for the last 5 years, we've won the Chairman's Award. And we made it to World Championships the last 6 years, and various other awards, quality, engineering excellence, innovation and control. I think we've been very fortunate to have strong students and strong mentors to carry us through. And it's going to be interesting to see what happens through the rest of this year and into next year as to the way things are going to go. But so far, we've been pretty successful.
I can go next. So we're a year younger than 3309. We've been around for 10 years right now. And I think we only have 3 regional wins in our 10 years in this area. We're actually not too good on a regional level. But I think where we really shine is going to champs in our iteration process. And we have 4 division wins over the last 10 years. So I guess that's our record right there.
That's fantastic. I think we're better we're just getting good at the regional level, I think. So probably since I started 2016, we made a regional final every year to present, and we got lucky to play this year, so we made the finals at Del Mar. We kind of were jinxed. We made 7 finals, and we never were able to. In fact, we were playing you guys, Evan, at LA, and we thought, how are we going to be jinxed? We were ranked number 1, and we picked Beach Bots, and we go, how is this going to go wrong? So the first match, Beach Bots dies. When do they ever do that? Right off the platform. So we actually, to make it, Evan can remember this, we went a 5-game final to win LA. I've never seen that.
I'm trying to forget that.
Hey, I mean,
you guys have
knocked us out in semis, so that's definitely fun to see.
So I should really say last year, 2019, the game, we got lucky. The game really came to us. Like I said, our software, our programming is a little bit wouldn't say weak, but we don't have the depth. So they didn't have Auton. So that really evened the field for us. We had the Sandstorm. So we're ranked number one at 2 regionals, Ventura and LA, got 2 banners there. And then when we got to Worlds, very surprisingly, we were ranked second in our division behind 254 and ahead of Blackhawks. But we can talk about that later. It's not because we have a good bot. I think it's some of the things we do and how we play and some of our strategy. But yeah, we're very fortunate last year. I don't think we'll ever have a season, like that again.
Wow, that's definitely in good hands today. We have very accomplished mentors today. So we have Rick Uval. We have another question. How do you attract other people to start mentoring your team?
As a mentor, I just ask, as many associates and friends that I have. You guys know, like Miles and Stu and things like that. So people that are in STEM or in tech or engineering. What we want to do is more like 3309 and Code Orange is get some of the younger alumni mentors. That's where the real life of the team needs to be. Those old guys can't. Evan can speak to this. We need that younger blood, right? That we can't be there every single day.
Yeah, it gets challenging. I would say alumni mentors are the key, and they bring in a younger perspective. They bring in a more intense knowledge of the game, have them having gone through it as students, and they're able to talk to the students at their level and contribute and understand their perspective, and also bring in details or ideas from other teams and the world community to integrate into their decisions without driving the team.
Yeah, I think that's one thing I was going to talk about. That's one area we need to improve is networking with other teams like yourself, and keeping that community open. I think having the young mentors help that. We have 3 or 4 returning alumni, which really help. They have some connection that way. But like during the season, you guys are very quick to pick up, like on, maybe you guys can start the West Coast intake wheels last year on the hatch intake. That's something we need to kind of implement a little more. One thing that we do a lot of, and I think can help a lot of other teams too, we do a ton of iterations. So I think on our hatch intake last year, we probably on our 8th generation by the time, the off season came around on that. So I think that's something to help rookie teams or other teams. Don't get married to your first idea. Just keep improving it, as you go along.
For us, in terms of mentor recruitment, we've had a lot. Sorry, there's an airplane above me. If it gets too loud, let me know. But we've had a lot of mentors come from UCI. So I went to UCI myself, and that's how I started mentoring the team. And I definitely echo what they both said about having alumni mentors. They've been the lifeblood of our team so far. And even a lot of our older mentors are alumni from the program from like 2002, 2003. And having an alumni perspective is incredibly important, we find, because it just changes how mentors interact with students completely. So we've done posts on Chief Delphi. We've had our friends from college come in. We've just reached out to different people we know, and we've gotten mentors from everywhere. So I think a good example is 294 though. 294 draws a lot of mentors from Northrop Grumman specifically. So if there's an engineering company in your area that you might have one connection to, a lot of engineers are willing to spend maybe an hour or 2 a week, helping high school kids, right? That's very attractive to people because they want to impart knowledge to the, people today. But that's how you draw them in, right? Have a very small time commitment at the beginning and then bring them in.
Yeah, and it's fun hanging out with all your friends, right? All the mentors.
Oh yeah, and free food.
Okay, going back to the records, obviously all of your teams have accrued very good records. What do you attribute to the team that has contributed to this success? You can take it from a general standpoint, or you can highlight a few more specific details.
I can go, I guess, for us. So like I mentioned a couple of times, we don't build the best robot. we're probably a top 10 robot in anything. We just don't have the experience or the depth. Again, my field's industrial design. So one thing we do uniquely is we focus on the user. So one thing we do probably have one of the best is if you look at our control panel. Our control panel is one of the most simplified and ease of use control panels. Like last year for the rocket, we had big diagrams of the rocket for the hatch and the fuel, and with big arcade buttons. So you don't see our drivers. It's make too many mistakes on it. I know when you use like a Logitech joystick, you got those little buttons on there. You see drivers doing things or going to the wrong thing. That's what we try to avoid. Another thing we do, since we can't compete with like a accurate shooter as much, we're doing pretty good on that, but we can't compete at the top of that. So we focus on some of the other points of the game where you get a ranking point like the climb. So we've been one of the top climbers, I'd say, since 2016. And going back to Worlds, we were surprised last year at Worlds, we were the best climber in our division. And we actually looked at the points. We were the best climber at Houston. Was our climber great? It was actually pretty slow. It barely put the robot on, but it was just ease of use. And another thing with climbers like this year, one thing that we do is we get a really wide range of engagement for the user, for the driver. So you see a lot of robots, they'll go up and their hook has about a 3-inch range. You have to be right under it and grab it. We shoot for like 2 feet of engagement. So the driver can be coming in at an angle 2 feet out. And that's not necessarily how great your climber is, but it's just something you want to build in, take into account for human error. I think that's part of, I think that's where our strength is, kind of more of a user-centric approach.
I can say on the fryer bots over the past few years, we've been able to make robots that can do most of the functions fairly well. And it does give you a lot of advantage when you're going into strategies. You have a lot of flexibilities in the strategies that you can employ. And also, you're not as much reliant on the alliance partners, and you're allowed to give the alliance partners different functions because you can do all the different functions in there. And sometimes some of the teams come in, they can only do one thing. So you're able to allow them to do that one thing, and they get a lot of reward out of that, as well as the team or the alliance wins the match. So we try to at least have the robot that can do as much as possible. And I know that's not something that we would recommend for rookie or new teams, but it's something that we're capable of doing, and our students are able to make happen.
I'm actually going to say the exact opposite of what Evan just said. I think our most successful years are when we did one thing incredibly well and everything else okay. I think a good example of this was 2015 for us, when we could only stack from the human player station. We couldn't deal with cans from the center. We couldn't deal with the landfill. But we just stacked really well, and that worked out well for us. I think for higher levels of play, it's important to be bulletproof. It's important to be your robot shouldn't ever break. It's important for your drivers to have incredibly fine-tuned muscle memory. So that's a lot of practice. And it's important that you're able to maximize what you can do on your alliance. So we all find success in our different places, but for us, I think the years that we tried to do everything were the years where we failed. The years where we picked one or two things to do really well is the ones where we excelled a lot.
We have another question here. How can teams use the off prepare used entered for the following build season?
You froze on my computer, Jack. She asked about what teams can do in the off season to get.
Yeah, how can they use it to prepare students for the build season? Different off season events or workshops, or what can they do from a mentoring standpoint?
I'll go. We don't have, because you guys probably have a much more formal program. What we've been focusing on, we didn't do it the first couple years, especially for new teams. Off-season events are incredibly critical, and they're really inexpensive. They're anywhere from $200 to $400 compared to 10 times that for, let's see. So we do as many off-season events as we can. It's not that, because it takes some commitment. It's really hard to do an event and do one the next week. But I think we did 7 events last year, including season and world. So it was grueling near the end, but you could see how much better the team gets. So I think by the end, we did Battle of the Border. I think we went undefeated all the way through, Jack maybe remembers, through qualifications and through playoffs. So that it really helps. And we learned a lot that way about maintenance on your robot, refreshing it and things like we didn't know before because we never played that much with the bot. So I think getting to do as many off-season events as you can.
Yeah, off-season is a very, very busy time for the Firebots. We co-host one Beach Blitz and also host the Battleship Blast. So a lot of stuff going on, and we try to use those off-seasons to encourage new drive teams, practice new drive teams, to get new people in the pits, to get familiar with how to work around the robot and where things are in the pit. And the rest of the off season, we try to do the training, make sure that the newer students are getting trained on the equipment and on the skills, so that they're ready to go when the season starts.
I'll echo what Rick and Evan said about off-season events. They're incredibly important. But for us, I guess I can focus on 2 specific areas. So for our CAD kids, right, we have all our new or interested CAD kids, right? They might not have done CAD last year. They might have done media or programming, and we have them all do the Symbotics tutorial series. And then after that, we partition little parts of the robot or different projects for them to try to take on. So that's kind of how we train our CAD kids during the off season. And for programming, if we have a completely new programmer, sometimes we actually have them recode the robot from last year from scratch. And that's a good way that we find that they're able to learn the skills because they have a good reference for them to look at because the robot code is already done. But it also allows them to run their code at off-season events. So it's a win-win in terms of motivation for doing something as well as having enough resources to help them get there.
Saikiran, how many people do you have on CAD in the off season?
I don't have a good number for that. I think it varies a lot. It varies a lot from people who are kind of working on stuff and people who are going really hard on working on stuff. So right now we have, I think, 4 kids doing a lot of CAD, but I know we have a bunch of kids tangentially looking into it. In the previous off season, we had maybe 10 or 12 kids who do the tutorial series, or up to 15. So it really depends on student interest.
So this may be a discussion for later on, but it's just kind of varying. So I know you guys are more of a community team. For our bots is a private school team. We're not really we're a public school team, but a public school district team. So we're a little bit larger. We can draw from 9 high schools, but we have to have a class. So we actually have a class that I teach. I'm in the process of becoming a teacher, which is very grueling. But so we actually have lessons. We'll do CAD. We'll try to do mechanisms that we don't know about and build in the shop and things like that. But we could always increase our depth and our, especially we need to recruit, I think, more across our district too.
Yeah, we usually have 4 or 5 students that are heavily into CAD, and there's probably 6 or 7 other students that are helping and learning while they go, feeding individual components to help build the assembly. So that's kind of how we go.
I see all the questions in the chat. We'll start addressing them slowly but surely. Feel free to keep dropping more questions too. We'll make sure to get through all of them by the end of the live stream. So we have a question, another question from Ali. Has COVID changed your approach to mentoring, and if so, how?
Well, that's a big one.
Well, we're sitting on a couch on Zoom meetings.
Yeah, virtual mentoring is one, it's not very much fun, and 2, it's I say it's very time consuming, and trying to do everything on the Zoom meetings. It's really hard to engage the students in activities over the phone. It's hard to get them excited about, how do you get them excited about learning how to weld or something like that when all you can do is show them pictures and things like that. So we've been having meetings three times a week, some updates, and working on some CAD skills, and work on some small CAD projects, and introducing some new technologies to the team. They're playing around with Swerve Drive just to play around with it, and we'll see where we go. We're doing some, instead of fabricating parts, we're having them 3D print parts so that they can have it in their hands and have that tactile feedback and experience trying to put things together. So that's kind of all we're doing right now. And every time we come up with a plan on how to get together, the environment changes, and we have to change our plans. So it's been kind of a long path to try to find a way forward.
So for us, it's been, I think for everyone it's been going a little slow. But what we're trying to do is focus on things we haven't had really the opportunity to do in the past. So we're notoriously bad at documentation, right? So what we're trying to do is encourage our kids to document our processes and make videos about what we do. So we think that's going to be helpful for other teams, but also be helpful for us a year down the line, right? When our seniors graduate and kids are like, oh shoot, what happened on the shooter last year? Or how does kickoff work for us? But we're also trying to, I think Evan's point about the 3D printers is important. We ordered a couple of printers and sent them directly to kids who are working on projects. And we're hoping that's going to be a good way for them to, get the tactile feedback, like Evan is saying, and keep them on task and forward on their projects. And we're trying to do the same with smaller electrical projects. We're trying to also build a Swerve drive base to give to a programmer and make it so they can fit it in their house. So it's a different sort of problem set that we're trying to deal with. But it's very hard for us to adapt. I don't envy any full-time teachers right now who are trying to figure out lesson plans for fall.
Yeah, what we did up until now, actually in class, since with robotics stopping, we actually designed, I think you guys saw, a bunch of COVID type projects. Different manipulator keys and UV light sources and barriers, but allowed people to use their engineering. And again, we did a bunch of people printed 3D. We have 3 machines that we're kind of rotating around. But I think now once we get past this and a little more in the summer, we are going to get more into training everyone more on SolidWorks and start doing some actual robot mechanisms. And also, I'm going to start talking about, I know there's been some push to talk about improvements for our robot, or this is something you guys can probably speak to too. Do you build another, I guess it depends on access to a shop. Are you planning on building a whole new robot right away? Or are you going to wait till see what the rules are? Or are you going to try and improve? You haven't played with what you have, right? So, so we have kind of a 2-prong. We're going to try and improve what we have. We had some issues with it last time, and there's also talk about building a whole new robot. So, I'm not sure. What are you guys' plans for that?
We're not sure yet. We're going to dabble with the Swerve Drive for a bit. If that turns out positive, that might be something we adapt into the current robot. We're looking at different improvements for the current robot as well. It'll just depend. It's going to be a challenge trying to avoid starving the students, especially the seniors, from their last year of being able to prototype and do those kind of things that they're used to doing. And so we might just go back and do some of that just to make sure that everybody gets a taste of that for the year, and we don't take that away from anybody just because of we already have a robot that works.
Our current plan is to iterate on everything we have right now, just make everything have better. So that's probably going to involve a lot of redesigning stuff, but same concept with Swerve.
Thank you, Ali Ahmed. Hopefully that answers your question. Stephen, hopefully that answers your second question. So, but as for your first question, we'll ask the panel. Stephen's question is, what has worked best for targeting the robot being done before end of the build? Do you do it before the bag? Do you do it before champs? Other?
I can start with this one. We are notoriously bad for finishing a robot right before our first event, which leads us to being incredibly bad at our first event. And I think it depends on what you're trying to go for. Sometimes for us, it's something we struggle with, but we have like a very unique, I guess, design process in terms of like we start CAD a little later after, a lot of prototypes are done. But I think we have a hard time like boxing ourselves into a corner, right? We don't want to like commit on like a drive base until we know that everything's going to fit on the drive base, or we don't want to commit to like a certain type of like shooter geometry until we know that like, oh, we can feed the shooter geometry. I think part of that is just kind of going back for part of what we did in the 2020 season is simplify everything a lot. So 2019, we like had a crazy robot that had like, 8 degrees of freedom and stuff, and that really hindered our season progress. So 2020, we decided to step back and say, hey, we think we can do some more complicated stuff, but we're not, so we can try to finish the robot earlier. And just being mindful of knowing your limits and knowing like, just knowing your limits is can help with the build season schedule problems.
The Saikiran, that's funny. That's not funny, but that's how we see you guys. We thought it was by plan that you start out, with a plan to get really strong, by Worlds. So we always thought you guys spend more time up front so you can have a better bot, near the end. We kind of do it both ways. On one hand, because we weren't as advanced as you guys have as part of our strategy, we try to work. We feel like we have to work harder than a lot of teams. Again, I don't know how you guys' work schedule is. We worked every day through probably the first or the second event with no days off. But we try to be strong for that first event because we know the good teams may be still developing to get that shot at Worlds. That used to be our philosophy. So we sign up for a week 1 or week 2 event strategically, so we can get that first one, then hope to improve and be competitive by the last event, a late event in the season 2, so we can be competitive there. But this year we did much more prototyping and development. This is more to talk to rookie teams or newer teams how to get better. So I think by the traditional bag day, we posted a joke. We had 4 frame tubes done in our say, yay, bag day. That's what we posted on our social media. We had nothing of the real robot done. So we spent many weeks this year working on wooden prototypes. I think that's important for newer teams. I think for our hopper, we went from something like a 6-second cycle time down to 1.8 seconds to reliably empty the hopper. And that was strictly through just tons and tons of wood prototypes and tons of iteration on that. So yeah, I think without the bag day this year, you can work a little longer. But again, I said I came from racing. I know you could have the best race car in the world if you haven't tested it and set it up before your event or adequate time to do that. It's not worth anything. A mediocre machine can beat you if you haven't had the time to stop it and get to a certain finish point before your first competition, and really go through it and make some revisions on it and refinements.
Yeah, this has been a real challenge for us the last few years in getting things ready in time for the first competition. This year we were actually behind and even finishing the second robot, so we were having to share the practice bot with the programmers and the builders at the same time. So it was a lot of late hours and splitting the days up. And as far as trying to meet a bag day, it's really kind of a trade-off as to what kind of value you're going to get out of the risk that you're taking to take more time. So we sit back and try to evaluate that. Let's see, this year we were able to get the drivetrain and chassis done pretty early, and then the rest of it was developing components. We tried to focus on one of the primary components, the shooter, to get that tuned up and working well, and while we were trying to get the intake working well, and that kind of thing. So,
Jack, I don't know if you are going to speak to it. I'd like to hear what these guys, teams do, how to maximize your competitiveness at an event. What's your event protocol?
So I personally believe that one of the most important things you can do at an event is scouting. I think that drive team wins matches, pit crew makes sure your robot can makes it to a match, but scouting is what wins events. And I think having a very robust scouting program leads to teams winning events consistently. I think Citrus Circuits is a very good example of that. Right? They have amazing robots, but by far. But they're so dominant because they pick the best robots and they know how to make their alliance work together. So I think that figuring out what's important early on, how to collect data early on, how to have a culture of good scouting on your team to make sure your data is good and your kids are happy and invested in the success of your program is incredibly important for being competitive at an event. And I know for us, for a fact, because we've managed to eke out a better pick than another alliance, we've won events. So that's something I'm very, I think is very underrated compared to a lot of other stuff, and is incredibly important.
Yeah, I'll say the same thing as Saikiran. Scouting, I think, is number one. Even pit scouting, a lot of teams will say a lot of things about their robot that you find out later are not exactly true, maybe a bit exaggerated. And then also, when you're going up for a match, to know from the scouting team whether the alliance partners, what their capabilities are, and also what your opponent's capabilities are, and how consistent they are, will drive what your strategy is for each of those matches, as well as give you an advantage for alliance selection. So I think that's, if it were one component, that's probably the most significant factor.
So one thing that we do, it's kind of the same approach. We try to maximize our ranking points so we can use our scouting to pick the best bot, to pick a bot better than us. So many times we find out we have a higher ranking than a lot of the other good bots. So we focus on that. So that goes a lot with our strategists. But so a couple of things we ask, and it's just more of a thought process again, like our team, before we even start, we ask, how many ranking points can we give up? And our answer, so everyone's score is 0. What happens, and typically your first one, you use that kind of as a practice thing. So we realized as we went along later season, when we didn't make as many mistakes, we'd go ranked from 30th to number 1. It's the same bot, right? So it's a huge difference in discipline for your drive team in the beginning. So one thing we focus at events is our drive team along with the robot. So one thing I see that we kind of focus on, every member of your drive team is pretty important. A lot of teams will stick someone they want to participate in the human player. So we try to make our human player the best human player there is, because it's a very critical, important position too. I know you guys do a ton of practice. We try to go. I think I don't know how much we show up at your field compared to other teams. We try to get there as much as we can.
It's as much as ours now.
So as far as competitiveness at an event, what you can do, I know one thing, our drive, we have a really good drive coach now. We finally have, like you are, Saikiran, a mentor, alumni mentor in there who knows the game, quick on feet. One thing we focus on is the end game, because it's the easiest ranking point usually. So we try to get that climb. One thing that makes us happy, if our bot's hanging there with everyone else and there's still 10 seconds left in the match, that makes us feel good. It makes us feel like we didn't risk that, trying to fill that rocket or something at the end and not get that second ranking point. So we kind of really focus on the ranking points. And just like you said before, robot preparedness, definitely newer teams, you got to have a checklist to go through your bot every time. I don't know how many times we've gone out there, it's something that we're not compressed or the battery's not zip tied. So we found checklists and a backup person for that. Really helps with that. Another thing is just that the team practice what we do. A lot of times they will be asked, when's the team dinner tonight? So our answer, Jack will know, our team dinner, when is it? We always say, well, when does pits close? It's 15 minutes after that. We know we're going to stay there and do everything we can to work on the bot, the time that we have. Same goes during matches. Not everyone goes to lunch until, some people can, but if something needs to be fixed, we try to fix that first before we take any breaks. Other match strategy we have is in the evenings when we're at away matches, we meet in the evenings when we do match vids. It's just part of the process. We really try to take this as a sport. There's a lot of, you let down your guard, once you go to the fun events, but you really have to, if you want to be competitive, you really have to keep those game practices up.
Actually, to kind of add on to this, there's something I just thought of that Evan was, we had the opportunity to have Evan a part of this. 2018 Orange County Regional, 3309 and us were, it was a great event. We were first seed, or first alliance, right? And we're, making our way up. And in finals, both of our robots kind of just died in our own different ways. And from that point, I think we learned a lot about how we need to deal with failure as a team. So what we started doing, right, is we started making sure pit crew members were at our drive team practices. So as soon as our robot died, it wasn't drive team that was fixing it, it was pit crew. And that made our pit better at fixing problems that happened at an event, right? They were able to say like, okay, we've seen this before like 10 times. We know how to fix it now. But additional to, onto that, right? Part of the reason why so in 2018 at that event, our arm gearbox just completely fell apart. Yep. The rest of our robot was working. So what we started doing, right, was practicing a lot of failure mode operation. So it's like, okay, if this motor comes unplugged, what do we do, right? If you don't have vision, how do you play the game? If your intake is broken, what do you do? And I think that really contributes a lot to your drive team being comfortable with new scenarios happening on the field and for them not to panic and freak out and to be able to adapt quickly on the fly. And I think that's very important for, being competitive on the field and, making sure everyone feels good and is doing, their best at the competition.
That was an amazing final. We weren't even there. We went to go watch you guys in the finals. And did someone's buddy climb get deployed during that match at the end too? Or I don't know who that was. Sorry, I wasn't sure.
Yeah. We drug it around the field for a little bit.
Everything that went wrong that match went wrong. Yeah. And we just had to get better at making sure things didn't go wrong. And if things go wrong, as they always do, how do we recoup from failed modes?
Yeah, our arm fell out at Worlds last year. Fell out of the elevator.
We're going to take the next few minutes to kind of wrap up. We're going to go a little bit over, but that's all right because it's the last workshop of the day. We have a question from Teddy from our own team. By the way, this is the last time to kind of drop in any last questions, so feel free. Teddy commented, when your team had a big leap in success, what were the largest contributing factors?
Want to repeat that again?
When your team had a big leap in success, what were some big contributing factors?
So our leap happened before I joined the team. I think this was between 2011 and 2012. So 2012 was the first time Code Orange won an event, and that was Code Orange's second year. And then 2013, Code Orange won a division as a third-year team, which was like no one knew who the team was. But what changed, right, was we had alumni mentor come into the team. His name is Andrew Hedge. He's also Woodie Flowers winner. But he was an alumni from 980, he mentored 968, and he was able to come to the team, show what could be done better, and inspire the kids to do better. So that's when our leap kind of happened.
Yeah, I think ours was, we had some of the alumni mentors came back and were able to help and strengthen the team and grow the team skills as well. So I think that was a big influence in 2015 or 16 timeframe.
Yeah, I think hopefully we're seeing that same trend. I think 2018, by the end of the season there, we were up near the top regionally. And I think that had to do with our alumni mentors coming back. In 2019, we had more coming back, but we need more from outside sources. But one thing that helped us out was we had I think this is good for rookie teams to hear. We had a water jet vendor that was really helping us out since 2016. So we were able to do a lot of parts quickly, but we really didn't want to push them too much by, saying, here's some parts, here's the same parts the next day with some changes. So I think it was, I don't know when we got our router. was it 2018? Yeah. So last year, 2019, we were able to iterate parts. That's one thing that if rookie teams want to know. We got an Omeo router. It's like $28 to go in. We have that thing running all the time. So we're, constantly generating new parts that night with design. So tons of iterations. So we're able to develop our bot much farther and quicker. So I think that probably the CNC router really helped us out. One of the most.
And then the last thing, any last tips for mentors or any other things that you'd like to cover as kind of a last note?
I can go. So number one, have fun. It's important for everyone to have fun, for mentors especially. I think I'm going to speak to two things kind of as an alumni mentor to other alumni who are looking to start mentoring teams. So college is the time where you're supposed to learn and have fun. So don't focus on FRC. Go do college things and have a lot of fun. But if you do, two things. One, I would not recommend you mentor your own team, and that's because of the second point, where as a mentor, you're not done learning. You're there helping students, but I've learned so much as a mentor, more than I learned when being a student. And I think it's very important for alumni mentors, especially, to go in, learn as much as they can. And if they want to help out their original team eventually, I think it's a better idea for them to go out, learn from other places, other sources, and then take new information back to the original team to make it better. So that's something I definitely recommend for any alumni mentors. If anyone has any questions about that, feel free to reach out to me.
Yeah, I would say for new teams or newer teams that just focus on having fun that first year and don't try to be so competitive. I want to try to make sure that all the students are engaged and they're having fun, because if they're not having fun, they might not come back. So that's kind of the emphasis. Search for opportunities for the students to explore things that they're really interested in first, and then start pushing them to do things that they're maybe not as comfortable with, and then also encourage them to try everything. I don't know how many times we found out that a student has a passion for welding, and at the beginning of the season or the first year they came in, they were deathly afraid of it because of sparks and whatnot. And now they're like master welders. So it's amazing how much the students will knowledge they'll gain, and they overcome it really quick on just trying different things.
I'd say to help any team at any level, really look at what your realistic capabilities are, and then build to that strength. Like Saikiran said, you can come up with some mechanism, one thing you can do really well if you're a beginning team. Don't try to do it all. And just work on your reliability and consistency. And, I think any team can do well with that. And just keep reaching out to mentors. I mean, there's a lot of them out there. I found at least dads and things like Evan and I are came from the same place. Or my kid was in it. But they're out there. They'd be willing to help, but they just need to be a little bit of coaxing.
Alrighty, thank you, panelists. We will have to wrap up today's workshop. Special thanks to Evan from Team 3309, the Firebots, Saikiran from Team 3476, Code Orange, and Rick from Team 5199, the Robot Dolphins from Outer Space. Tomorrow, the summer series will continue at 5 Pacific time with a programming workshop. Please check our Instagram at Robot Dolphins for more information and details about the workshop we will be hosting throughout this week. Also, please subscribe for easy access to the stream. This has been Jack Fallon from Team 5199. Thank you to our panelists, and thank you for tuning in. Bye-bye.
Thank you, guys. Continue.
Thank you, guys. You guys are doing awesome.
Thank you.
See ya.